I'm Etienne Chocho, and I'm going to talk about the journey we had building a new Spark runner based on the Spark social streaming framework. A little word about myself. I'm a senior software engineer at Talent and an Apache Beam committer and a PMC member. At Talent, we do data integration software that basically allows users to create processing pipeline by assembling UI components without coding. In that case, it's a pipeline designer tool, which is a big data designer tool that is based on Beam. The agenda for today will be a quick introduction to Beam, for those of you who don't know it, if you did not attend the previous talks. And I will focus in this introduction on some of the Beam model concepts that will be needed for the continuation of the talk. I will do the same introduction on the Spark social streaming framework, and then I will dig into the subject of asking why was it worth creating a new runner with this new Spark framework. And then dig into some details with the overall architecture of the runner, some implementation points that were interesting, and usual current state and future work. And I will conclude with lesson learned and a Q&A session. So, to introduce Beam, I will just say that Beam is a programming model that allows to build big data pipelines, and it's unified between batch and streaming. That's because we believe that there is no real distinction between a batch pipeline and a streaming pipeline. The only difference is that a streaming pipeline will deal with an infinite collection of data, and batch pipeline will deal with a finite collection of data. So then, the batch pipeline can be seen as a subset, indeed, of the streaming pipeline. And all you need is to divide the data into chunks, and that's why Beam provides windowing. This is the Beam stack. On top of it, you have the user code, so that's the pipeline written by users, using libraries of transform, IOs, provided by the language SDK. There are several language SDKs for Java, Python, and Go, and they expose the Beam model, actually. And what's the focus of interest of this talk is the bottom layer, the runner part. That's the translation between the Beam API and the native engine API. In our case, Spark, but there are several runners, more than the one that are shown there. The Beam transforms, actually, there are only 3 Beam transforms that are primitive ones. There is the Pardue, which is the usual flat map, the Google flat map. There is the group by key, which allows to group data into groups to be processed later on in parallel, and the read, which inputs data into the pipeline. And actually, all the other transforms in the Beam SDK are composites of Pardue and group by key. Even the reduce, which is called combine in Beam, it can be seen as a composition of Pardue and group by key. This is the usual example, very simple one, very straight one, of reading text file and counting the occurrences of the word. This is there just to show you the Beam API. So we have access to the pipeline for the user with the pipeline object. We have an abstraction of the data amongst the cluster, which is the collection, and a collection of, collection not the correct word, but a set of transforms like IOs, for example, text IO, to read and write from Google storage in that case, and flat map, count, or map element. This is the Beam vision about portability. Like there were some talks, the previous one and the one this morning, I will not focus on that, just say that we can use whatever language SDK to run on whatever engine, no matter the language of the engine itself. So I will not dig more into that subject because this is not the purpose of the talk. Either I will focus on a first key model concept that will be needed for the continuation of the talk. It's windowing. What is windowing? Windowing is a way to group elements based on temporally and based on the event timestamp. The event timestamp is the time in which the element was produced, and this windowing is mandatory for streaming because you need to divide the infinite data, and it's also available on batch because you can apply timestamp to your data and then apply windowing. That's optional. We provide several kind of windowing. The fixed window, which allow to express things like I want to have the last 30 seconds of data, or sliding window, which allow to express things like I want to have the last 60 seconds of data every 30 seconds. Of course, in these diagrams, it's showing keys, but it works. That's a general case, but it works on P collections that have no key. We also provide session windows. Session windows are quite similar to web session, as they are defined by a gap duration, meaning that if you don't receive data for something like 30 seconds, then the next element will be seen as belonging to the next window. So that's for the three main windowing capabilities. We also have a global window, which is basically the default windowing that you get when you don't specify a window. This window contains all the elements, all your data, and it's useful for batch. There is also something more generic that allow, and that's important for the continuation of the talk, we have what we call custom window. That's what is available to the user to programmatically say, for a given element, it should belong to this or that window. Another key concept is watermark and late data, which are linked. In a streaming system, actually, you always have lag between the event timestamp, so the timestamp at which the element was produced, and the processing timestamp in which the element was received by the system or processed by the system. And also there is out of order data. And for those two things, we define watermark. So what is watermark? Watermark is the point in time when we should not receive older elements. If I said it another way around, it's the system notion of when all the data for a given window can have expected to come. So I'll take an example. If I take a very simple watermark, very naive static watermark of a lag of 10 minutes, then at 2:10, the system will consider then no element older than 2 can arrive. Simple. You must know also that the watermark in Beam is set by the source and is propagated throughout the pipelines with the transforms. And we also define late data. What is late data? Late data is data that arrived after the watermark. So in my previous example, if you have an element with a timestamp of 1:55 that arrives at 2:15, then it's more than 10 minutes late. So it's behind the watermark, so this element should be dropped unless you specify a load likeness. That's a tolerance that you can add, let's say, 10 minutes, so that this element could not be dropped. Another important thing in the Beam model is triggering. Triggering is what tells Beam when to output data. The default trigger is, you don't need to specify this one. It's when you specify no trigger, you get the default trigger, which is when the watermark passed the end of the window. So at that moment, it is when this watermark passed the end of the window that the output of computation for the window will be sent output. So in my example, if I have a fixed window of, let's say, 1 hour, so if I have my watermark of a lag of 10 minutes, then this window will close at 2:10. Simple. There are several types of triggers. There is the event time-based triggers, so that's the one I was talking about from the beginning. And there is processing time triggers that are based on the time in which the elements arrived in the system, and data-driven triggers that are based on the number of data arriving in the system. The triggers also allow us to have previews, like having early preview results before the window closes and late results after the window has closed. and they are composable as well. So that's it for the Beam Mo introduction. I will do an introduction on the Spark structure streaming framework as well. So this framework is not that new. It was released in beta in 2.0 of Spark in July 16. It's based on Spark SQL, and it provides an important thing for us is a unified batch and streaming API, which is called dataset or data frame. It has type and schema enforcement because in datasets, the datasets know the structure of the data, so there is enforcement of these schemas, but it's still micro-batched. They provide something called the continuous processing mode, which is there for low latency streaming pipelines, but unfortunately it does not support any aggregation, so we cannot use it for Beam. So we will still be micro-batched in our case. And one important thing also is that it has an optimizer, which is called Catalyst, and which is basically like a SQL optimizer. It optimizes the execution plan of the Spark queries. All in all, this framework is quite similar to Beam, right? We have event-time windowing, which is kind of different because they only provide fixed windows and sliding windows, and it is quite different from Beam. We will see this in the implementation feedback later on. They have watermark support also, but once again, this one is quite different from the Beam vision of the watermarks. We will see that later on also. They have also triggers to output data, but only at the end of Windows. They don't have these database triggers, these processing time triggers, and all these things. And one last thing is that they have streaming sources that have offsets that are checkpointed for tolerance. So the big new thing with this new Spark structured streaming framework is that data arriving in the pipeline is seen as an unbounded table. Actually, as data arrives in the pipeline, it's appended to an infinite growing table. And this table gets applied incrementally the query defined by the user. So that it updates a temporary result table, and this result table gets output when the trigger fires at time 1, for example, or at time 2. If I take an example of that, of a streaming pipeline reading netcat and reading animals' names and counting the occurrences of these animal names, if between the start of the pipeline and time 1, if you receive cat, dog, 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 then these 3 words would be appended to the input table. The count query will be incrementally run by Spark on this input table. The result table in green will be updated with cat 1 and dog 3. And when the trigger fires at time 1, the output would be done of the result table, of course. If you receive between time 1 and time 2, you receive 2 more words, all and cat, then they will be appended to the unbounded table. The query will be incrementally executed. So cat is now 2 occurrences, dog is now 3, all is now 1. And then when the trigger fires at time 2, you will have the output corresponding to the result table. So that's it for the introduction. Now the big question. Why was it worth creating a new runner based on this new structured streaming framework of Spark? That's because it provides some useful things to the Beam project. First of all, like I said, the unified batch and streaming API. There is no more RDD and DStream distinction. We previously had a translation based on RDD for batch and streaming and DStream for streaming. So there's no more difference now. It's only the datasets API. And that's useful for Beam because Beam has also only one definition of the collection, which is the P collection, no matter what, if you are in batch or in streaming. Also, it has better state management. There is now an incremental state saving, and also no more synchronous saving of the states that delays the pipeline. an important thing is that they have schemas in datasets. So Spark datasets know the structure, the fields of the data, and can then optimize later on this structure. Also, as we have also schemas in P collections in Beam, then we could leverage the Spark schemas. They have also a good new source API that is very close to Beam. We close to the bounded and unbounded sources of Beam. And also they have even time windowing and watermarks, but as I said, they are quite different than the Beam Vision, so I will focus on it later on. So now that I explained why it was worth leveraging some of these features, why should we make a runner from scratch? This is because the structured streaming framework is very, very different from RDD and DStream, so there's no point reusing the code that was written for such a different API. And also because we hope to gain some things, like a more up-to-date runner in terms of libraries, to be able to leverage these new features that I presented. Also leverage the learned practices from the other runners. Also a better performance thanks to the DAG optimizer, and obviously try to simplify the code and ease the maintenance. So now I will dig into the technical subject of interest, which is the runner architecture. So you remember my introduction pipeline, very simple, that counts the words. Actually, the Beam SDK construct the equivalent of this Beam code as a graph, which is on the right-hand side, which is a direct acyclic graph, a DAG, that contains only Beam transforms, like read, flat map, count, map elements, all right. Okay? And this is what goes in input for the runner. The job of the runner is to translate the blue part into Spark native code. Of course, this is pseudocode, you see, but it's using the Spark native API, like the Spark session, the read with data source v2 API, flat map, aggregation, and so on. So this is this native Spark code that gets executed by the actual Spark engine. So how is it done? Actually, you remember in the introduction, I said that there are very few Beam primitives. And in that graph, there is only one actually. There is only the read one. All the others are, let's say, implemented by the Beam SDK as composites. Flat map element is a Pardu. Count is a combine Beam transform, which is itself a composition of group by key and Pardu inside the SDK. Map element is also a Pardu, and write is a Pardu. Okay? And what the runner does is, first it detects the translation mode, batch or streaming. That's mainly to know which kind of source, which kind of Spark source it needs to create, and which kind of action it needs to run on the output dataset to run the pipeline. In that case, it's a for each action, so that's a batch pipeline. There's no data stream writer and all these streaming things. So that's it for the mode, the translation. Also, when the runner visits this DAG, it can choose the translation level he wants. That's the green boxes. So for the read part, there's no point. That's a primitive, like I said. So there is a direct translation from the Beam read to the Spark read using data source v2. That's simple. And Pardu, it also a primitive. So there's a direct translation of the Pardu as a Spark native flat map. But for combine, actually, we could have translated the group by key by a native Spark group by key and a Pardu by a native Spark flat map, but it would have been less performant than choosing to translate at the combine level. That's because the combine as a direct Beam combine as a direct equivalent in Spark, that is an aggregator. So that's more performant to use the aggregator. And when the runner visits this DAG, you see that it creates an input dataset out of the execution of the read. And this input dataset gets applied the Pardue, so the flat map, as an output. The output of applying the flat map is used as input, and the output of this one is used as input for next step, and so on, so on, so on, and until we run an action on the last dataset to execute the pipeline in Spark. So that's it for the overall architecture of the runner. What I wanted to give here is implementation feedback on some interesting point while implementing. So the first is windowing. You remember what I said in the introduction on windowing? And what we can say in the translation of windowing is that Spark windows are only based on an interval in even timestamp and support only fixed and sliding windows. They don't support session windows that we have in Beam. Also, Beam windows are more generic. You remember I said in the introduction that user can provide code to tell for a given element to what window it should belong, right? So in the end, the Beam windows are quite more generic than the Spark ones. So we cannot rely on the Spark windows to support the whole Beam model. So as a consequence, we will need in the translation to manually merge the windows. And as another, when we have aggregations, we only merge the windows on aggregations like group by key or combine. And as a consequence to that is, to be able to merge, we need to have the window representation alongside with the element. So we need to store in the dataset the Beam window representation. And that makes it very difficult to apply Spark schemas, because we will need to encode both the data and the windowing information inside the Spark schemas. So that's it for the windowing specifics. Now for watermark and aggregations. Actually, lucky us, we have common definition. Between Beam and Spark, there is a common definition of the watermark notion. That's the system notion of when all the data in a certain window can be expected to have arrived. And also, closing a window means for both when the watermark passes the end of the window, like I said, with my example of the 10 minutes like watermark. But there is big differences in watermark between Spark and Beam. Spark is based on the newest timestamp, and Beam is based on the oldest timestamp. So that's quite a difference. And there is even more a huge difference on scope, because Beam scope of watermark is per transform. There is a watermark value for each transform of the pipeline. And these watermark values are updated as the data arrives in the streaming pipeline. For Spark, that's very, very different. They have only global watermark. They have only one value of the watermark, no per transform watermarks. And the way it works is that, as I said, it's microbatch based. So at each end of microbatch, Spark will update the global watermark and use this new value as input for the next step. That's it. But that generates a big problem. Actually, structured streaming framework for now cannot support more than one aggregation on a streaming pipeline because it has only one value of the watermark. So that's a problem for us because Beam supports multiple aggregations in streaming pipelines. So once again, we cannot rely on watermarks, on Spark native watermarks to support the Beam watermarks. We will need to use manually deal with them. And another consequence, there is an open ticket on that in the Spark community, and we're waiting for the community to support these multiple aggregation in streaming mode. I know that there is a design ongoing in the Spark community because we helped commenting and helping designing them, but it's still not supported. Another feedback is combiners. You remember I said that the combine has a direct translation in the Spark natives as an aggregator. And actually that maps really well. Both define a commutative and associative function that defines how to initialize an accumulator, add an element to the accumulator, and merge the accumulators between each other. So that's the usual combine definition, and we share the same definition. So that was easy, a one-to-one mapping. But there is an exception. The exception was the combine globally. Combine globally is the Beam transform that says, I want to combine, but I have no key. I have a P collection with no key. And the problem is that Spark needs it needs groups to aggregate. So either based on the column groups or key groups. And it could have been translated, the combine globally, as a native group by key and then a native aggregator. But it has proved not that performant, and it was better to use the Beam SDK composite translation of what is a combine globally. And this composite translation is applying fake keys to the P collection so that you have keys, and then calling the above translation, which is combined per key. And why is it better performance? Is because the Beam SDK adds what we call fan-out. Fan-out is a way to reduce the load of the reduce phase by avoiding having big groups of elements when we have few keys. And by benchmarking them, this translation is better. So that's it for the combine. An easy one, sources. I said in the introduction that there was in the Spark social streaming framework a continuous processing mode for low latency streaming pipelines. But as I said, it doesn't support aggregations, so we're not using it. We're still using microbatch based sources. There is microbatch based sources in data source v2 new API of Spark. And easy way. We once again share the common definition of what a source is. We can define in data source v2 how, and Beam also, how to split input data. And we also define a common reader that is responsible for sending the next element. So it's a one-to-one mapping between Beam and Spark. Another big complex topic is Spark SQL catalyst optimizer. Its job is to iteratively apply rules on logical plans to end up having better performance, end up with physical plans like the SQL database, and this physical part will be used to execute the pipeline. So this catalyst has two entry points. You can either come from the SQL query, that's when you write your pipeline using Spark SQL, but this is not our case. And you can enter by the data frame or dataset API. Then you get the unresolved logical plan, that is the output of parsing. So that's basically a logical plan with empty references. Then after the analysis, it gets the references filled, and then it applies rules to optimize this logical plan, and end up having an optimized logical plan, and then Catalyst applies native Spark transforms, and end up having physical plans. And after that, it applies a rule to cost these physical plans to choose the better, and then comes the code generation time. Actually, the Catalyst plans are made of Catalyst expressions. And Catalyst expressions contain Java code. And when the Catalyst is executed, this Java code is generated, compiled, and executed. That's it. And why am I tailing all these details? That's because at some point within the Beam community, as I said, we were very different between Spark and Beam with watermark and windowing. I said that they were not very compatible. So at some point in the Beam community, we said, shall we use a lower level interaction point with the Spark engine? So shall we connect, let's say, at the unresolved logical plan level? Because if we cannot support windowing and watermark, then maybe there's no way, there's no point using the data frame API then. So we were kind of thinking, but after a discussion with the Spark community that time, it appeared that Catalyst is quite internal to Spark. So that would be very risky to depend on Spark internals. And also that would be, Spark community said that would be very hacky to try to connect to that. So we end up avoiding that, and we still write our translation pipeline using the dataset API, so we enter by this entry point. Another key implementation feedback is Spark schemas and Spark encoders. First of all, what are Beam coders? Beam coders are a way to serialize and deserialize data. So you get an object, you serialize it to a bytes array, and you can read the bytes array and unserialize it to the object back. So that's similar to the Spark encoders, right? And what are Beam schemas? Beam schemas, that's a list of fields with name and types, and it's pretty much the same as database definition, right? These schemas in Beam are optional. You can have P collection with schemas, P collection without schemas, contrary to the Spark framework where the dataset, it's mandatory on datasets to have schemas. We can apply transforms that are schema aware. So if you filter, you can filter on a given field of the object. You can also join on this special filter of the on this special field of the object. Beam also provides what we call a row. Row is basically the element plus the schema. So that's the structure element. And we provide the equivalent of a coder with schema coder. So that's a coder like this one, but instead of using bytes array, it uses row as input and output. So all in all, Spark row and a Beam row are pretty much the same. And a Spark schema and a Beam schema are pretty much the same. So how do we link them? For encoders and coders, actually we had to wrap Beam coders into Spark encoders so that Spark could leverage Beam coders and call the user-specified code. But that is quite tricky because a Spark encoder is a catalyst expression. That's why I gave the introduction on the SQL catalyst optimizer. And this catalyst expression contains Java code. And this Java code, when catalyst runs, it generates it, and this is this code that calls the Beam coder. That's pretty simple. And for Spark schemas, unfortunately, it's not wired yet. We only tell Beam that we provide bytes. We say as a schema that it's only bytes array, so it cannot tell which fields are in the data. So the next step for this schema wiring will be to create a schema for Beam, but as I said on the windowing part, as we need to merge the windows, we need to store the windowing information alongside with the data, so that means that we will need to encode the data plus the windowing, the Beam windowing information into a schema, and that's why it's not done yet. So that's it for the implementation feedback. I will do the current state and future work usual things. So what's the state of this new structure streaming runner? Only batch mode is done, and it's quite advanced because it passes 89% of our validation runner tests. The streaming mode is barely started. That's mainly because we are waiting for Spark multiple aggregation things that I was talking about. Also, the runner can execute nextmark. So what is nextmark? Nextmark is our internal performance framework, and it's actually simulating user pipeline of an auction system. It creates an auction, people connect, and they place bid on auctions, and you can ask questions to this system. So if you want some more details about nextmark, you can see on my LinkedIn page the talk of 2017 in Miami about nextmark. What's important about nextmark is that it covers 100% of the Beam model, so that's a pretty good performance framework. Some things are not wired up in this new runner. As I said, we are tricking Spark with schemas by saying we are only sending bytes. And also some of the optional features of the Beam model are not implemented, like the state API, like the timer API, like the splittable Doofen API. We have not implemented them yet. And what's the focus of our work today is performances, and also because they are quite new, there's been coded like something I did say on Friday. So the new Spark encoders are not called already. It's called at some places in the runner, but not yet in all the translations. So I wanted to give some first perf results. Actually, it's quite early. It's not a production-ready runner, so that's very early stage, but I wanted to show you. This diagram is a nextmark execution. So you remember, it's an auction system, you have some queries, you ask questions to the system. So we run these nextmark things on the two runners by generating 100,000 events on the local Spark engine with 4 threads. So in blue, you have the performances, the response time for each queries for the new Spark runner, and in red, you have the response time for the current production-ready runner based on RDD and DStreams. So all in all, what we can say is that the new runner is basically 10% slower than the other one, than the current one. There are some points where it's more performant, like query number 5 or query number 14. And there are places where it's way less performant, like query number 4 and query number 7 that we are working on. And that's quite normal that the performance is not that good. That's because, like I said, it's a very early stage. It has not received a lot of attention yet, comparing to the current runner that has received something like 3 years performance improvement. So that's it. That's normal that we don't have this performance right now. Also, there are leads for performance improvement. As I said, Catalyst, it can only apply rules of simplification of the tag. So there is still Catalyst optimizations, but not at the field level. And one tiny thing also is that as we serialize the old data, sometimes, for some cases, it can be counter-performant. Because if you had to, let's say, filter on a given field, then there's no point serializing all the data. You serialize just the field, right? So that's it for the performances. I will then put back this Spark runner inside the Spark runner ecosystem, because if you've been to the other talks, you should ask yourself a big question, which is, we have 3 runners, actually. That's fun. We have the structure streaming runner, which is the part we are talking about, and we have the current production-ready runner that is based on RDD and DStreams. This one is, like I said, the production-ready runner. And it has received a lot of performance improvement. Like I said, if you need some more details, you can see David Moravec explanations at last Beam Summit in June in Berlin. So that's 2. And that 3, this morning, if you were to the talk, you heard about the portable Spark runner. So this one is like the previous talk about portability between the language SDK and the engine, but it's still based on RDD and DStreams. So that's another runner. Right now, like it was said in the previous talk by Max and Thomas, it is only batch mode, and it's almost complete in features, and it can run any language, Beam language SDK to Spark. So here comes the big question. We have 3 runners. How do we unificate them? That's a very hypothetical plan of mine, right? First, we will wait for the multiple aggregation support by the Spark community. Once we have that, we could code the streaming part of the runner. I said that it was almost not done, not started. Then we will have all the validates, the Beam validates runner pass. I mean, at least for the most important features, not the splittable Dufen, timer, and state APIs. At that point, we will have a new runner that could be pushed to master, because right now it's a feature branch, and we will get some user feedback, right? And that will lead us to fixes and to performance improvement. And once the new runner has at least the same performance as the current one, production-ready RDD DStream runner, we will have a new production-ready runner. So that will make 2, but in the end, we will need, in the blue one step, to merge the portable layer that was done, but with the new Spark structure streaming runner. And at that point, there will be a new production-ready runner based on structure streaming framework, so we could drop RDD and DStream-based runners. The current one, not portable, and the portable one. So don't ask for dates. Before the Q&A sessions, I will do the lesson notes. Actually, there were some pain points and some sweet points in the translation. The pain points were that the structure streaming framework is very, very user-oriented. I mean, for example, to be able to instantiate a Spark source by passing it a Beam source, we had to serialize the Beam source to a string. That's because the Spark source APIs only take strings as input, because it's very user-oriented, so that's kind of hacky. Also, I gave all the details on the catalyst part, because that was a pain. Actually, catalyst expressions to wrap the Beam coders, like I said, well, they contain Java code generation, so that's kind of difficult, and there is no documentation on these catalyst expressions, and there is no Java API. So you have to, let's say, bridge with the Scala to call these APIs, because the runner is written in Java, and Spark Engine is written in Scala. Also, some of the concepts are more static in Spark than in Beam. The triggers that I presented, the windows, and the watermarks. And some of these concepts are called the same, like watermark, but they are completely different. You remember the newest timestamp vs the oldest timestamp, and the scope pair transform vs the global watermark, right? This is not the same at all. And one final thing, we still lack the support from the Spark community of multiple aggregation in Spark streaming. So that was the pain points. Luckily, we had also sweet points. These sweet points were that, first of all, the structure streaming framework provides a very good API that is both for batch and streaming, that's unified, and that is the dataset API, right? some parts of the Spark API map really well with Beam. You remember I said that sources map one-to-one easy, and combiners map one-to-one easy, right? And schemas also that are available now in datasets will allow in the future to leverage the Beam schemas. So that's it. I will give some references. For the structure streaming part, like I said, it's still in a feature branch. So if you have suggestion, ideas, or something, feel free to submit a pull request to that, and we could review it with pleasure. Also, there is the structure streaming design document that explains some of the key choices that were made on this new runner. You should also join the Beam Spark channel in the ASF Slack, and also join the mailing list, the user and the Dave mailing list. And of course, maybe follow us on Twitter to have some updates. There will be plenty of good talks later on. Of course, I could not put all of them because I have only room for 4. But, well, these are some of the good talks that you will have later on. That's the end of my presentation. I think I've almost no time, so maybe time for a question, maybe one. So feel free to ask.